All right, what I want to work on today is to work on some carbonyl problem-solving strategies. I've been talking to some people yesterday and today, and it's clear that some of you are having some issues trying to figure out where to start these problems, where to go once you've gotten started. And so what I want to do is work through some of the things I think about when I do problems like this and give you some problem-solving strategies that I hope will help as you work on the homework that you're doing for Wednesday and as we continue to work on more reactions of carbonyls. All right, so I wrote down a bunch of ideas that I had in terms of problem-solving strategies. I want to walk through this and then do some problems and show you how I look at doing these problems. All right, so again, carbonyl problem-solving strategies. There are three types of carbonyl problems that we're going to see, and essentially reaction problems in general. Number one, predict the products. Number two, provide a mechanism. Number three, provide a synthesis. And the proposed synthesis ones are the most challenging, and we'll work through those, and those will be the most difficult ones, right? We'll get to those in a minute. What I want to start with is how you predict the products, what strategy we use for that. All right, so here are 4 steps that I hope that you would work through as you're doing these types of problems. Right? Number one, does the molecule have an acidic proton? Always look for this first. Acid-base reactions are going to happen faster than carbon-carbon or carbon-hydrogen bond formation. Right? So if you have a carboxylic acid or an alcohol, you're going to get an acid-base reaction first. All right? So don't forget to look for that. Right? You'll get deprotonation of these things, right, before anything else will happen. 2, what type of carbonyls are present? 3, does my nucleophile react with that type of carbonyl? Right? If you have sodium borohydride in an ester, you're not going to get a reaction. Right? So make sure that it's clear that whatever you're using for your nucleophile is going to react with the carbonyl that's in your molecule. 4, if yes, work through the mechanism to determine the product. Right? And again, we have some very clear mechanistic options for the reactions we've been looking at. Is it addition? Right? There's no leaving group in the tetrahedral intermediate. Stable until addition of H+, so that's going to yield alcohols. Is it substitution? The tetrahedral intermediate has Cl- or OR- leaving groups. If that's the case, reform the carbonyl and react again with the nucleophile. We've seen this in the case of acid chlorides and esters. Also, don't forget we have some unusual mechanisms, right? I would say right now we have 3 unusual mechanisms, right? We have a carboxylate anion plus lithium aluminum hydride. That yields a primary alcohol. And if you work through that mechanism, you see we have this interesting O- to aluminum hydride leaving group, right? Similarly, in amide plus lithium aluminum hydride, we get to an amine. Same strange leaving group, and we work through that mechanism in class on Monday. Right? And then the third one is a carboxylate anion plus an alkyl lithium, which gives us a ketone. And again, that goes through this hydrate intermediate, which we said is unstable, reacts to give a ketone in water. And that's a mechanism that you're working on to bring to class on Wednesday. Right? So what I want to do now is I want to work through a problem sort of thinking about all of these strategies, these steps, right, and show you how I would do it. All right, so here is a problem that I think is a pretty interesting problem. All right, so let's take this molecule, right, and react it first with methyl magnesium bromide, followed by an acid quench. All right, and again, this molecule might look a little strange to us. It's a ring. I know sometimes we get a little intimidated when we see rings. Right? But looking at this molecule, it's simply an ester. Right? It happens to be a cyclic ester, but it's just an ester. Right? So if we look at this, go through our steps. Number 1, are there any acidic protons around? There are not. There's not an alcohol. There's not a carboxylic acid. Number 2, what type of carbonyl do we have? We just said it's an ester. Number 3, does our nucleophile react with that type of carbonyl? We have a Grignard reagent that definitely reacts with an ester. Right? Number 4, let's work through the mechanism. All right, so we have our carbon-magnesium bond making carbon electron-rich. That's going to attack the carbonyl. we get our tetrahedral intermediate. We look at this tetrahedral intermediate and say, do we have an O- or Cl- leaving group? And we do. If we reform the carbonyl, and again, we're going to reform a different carbonyl than the one we started with, we can break the bond to the O- leaving group. So we get to that compound. Now we have a ketone. We can react again with the Grignard reagent. We can look at that tetrahedral intermediate and ask, do we have any O- or Cl- leaving groups? If we look, we see here the only leaving groups we could possibly get are carbon minus. So that is going to be stable. There are no other carbonyls, no other reactions that we can do. So this is the time where it's appropriate to add acid. And we can have our alcohols form in the final step. So a pretty interesting reaction in which we had a cyclic ester, and now we've converted it into a diol upon reaction with methyl magnesium bromide to add 2 methyl groups. Okay? So again, working through our strategy for predicting products. All right, what I want to do now is to work through how you provide a mechanism and how you propose a synthesis. We're going to start to see a lot of proposed a mechanism problem, all right? And let me just go through some general strategies for these mechanism problems, all right? Number one, we've done this in class. I want to continue to encourage you to do this. Number the atoms, determine bonds formed and bonds broken. Number two, as always, think about what's going on, all right? Think acid-base, electron-rich, electron-poor, good leaving group, octet rules, all of those things. Make sure you're thinking about that when you're working through the problem, right? So when working through problem, think acid-base, electron-rich, electron-poor, good leaving group, octet rule, etc. All of the important steps and concepts that we've been talking about this semester. All right? And then finally, and I hope this is clear from what we were doing, we're always going to use curved arrows to illustrate what's happening in these mechanisms. All right? So use curved arrows to illustrate electron movement in each step. Okay? So let's look at a mechanism just to work through how we would do this. Right? So one question would be, given benzoic acid, provide a mechanism for the reaction of benzoic acid with lithium aluminum hydride followed by acid to yield benzyl alcohol. Right? So this is a very common question, common type of question. How would we approach this? Right? Well, first we're going to number the atoms to determine bonds formed and broken. Right? So hopefully it's clear that if we number this out, we have the same number of carbons. Right? So if we look at the bonds that are formed and broken, hopefully it's clear that those CH bonds are the bonds that we're forming. All right, so we're forming 2 CH bonds, right? And we're breaking the carbon-oxygen double bond, right? And I think it's really important for us to determine where did the oxygen end up, right? I think that's especially important. Okay, so when we're thinking about this mechanism, again, we need to remember the things that we have listed up here: acid base, good leaving group, octet rule, all that stuff. All right, so the first thing that we should think about is we have a carboxylic acid. Carboxylic acid is always going to look to donate that proton. We have a good base with aluminum hydride, so that's going to be the first thing that will happen. We're going to grab that proton. We're going to generate hydrogen gas. Plus a carboxylate anion. Right, now that we have the carboxylate anion, that's going to react with lithium aluminum hydride. Add a hydride to the carbonyl, making the first of our 2 CH bonds that we need to form. And just like we talked about in the reaction with an amide, this is where we're going to have this Lewis acid-base reaction to form an oxygen-aluminum bond. Now we have an oxygen that can leave as O-, so we can reform the carbonyl. We generate an aldehyde, another reactive hydride species, which can donate H- to the carbonyl. That enables us to form our second CH bond. Now we have something with a tetrahedral intermediate that's completely unreactive, and that's going to be stable until we add acid. And thus we've worked through the entire mechanism. We've used curved arrows to illustrate all the bond breaking and bond forming steps, right? And there's our complete mechanism to answer this type of question. Okay? And then finally, let's look at how to propose a synthesis. All right, we've done a couple of these problems in class, and you're working on some of these problems for homework tonight. All right, so the first thing that we should be looking for when we're proposing a synthesis is to look for retrons. And again, retrons are functional groups you know how to make. Right, so for us right now, we know how to make alcohol, ketone, carboxylic acid, and amine functional groups, right? And the key thing here is that we must know the reactions that we've learned backwards, right? So that's a really important point. It's not enough just to know the reactions A plus B goes to C. You have to know C can be made from A and B. right? So make sure you're studying those in reverse. Number 2, work backwards, right? Focusing on breaking bonds to yield the starting materials you need. Right? And then finally, 3 is to write out the forward synthesis critically evaluating each step. Right? And so let's just work a problem just to highlight what we're doing here. So here's a common type of problem, right? We have our target propose a synthesis from 6 carbons or fewer, and that's all the instruction that we get, right? So here's the molecule that we want to make, and if we look at this, hopefully we're looking for retrons. We see that we have a secondary alcohol, right? So that should be the first thing that we think about, right? When we see a secondary alcohol and we're thinking about making a carbon-carbon bond, we should be thinking, we're going to add a Grignard or alkylithium to an aldehyde. That's the key reaction to make a secondary alcohol. And we're going to think in the reverse direction. And we're going to recognize that for a secondary alcohol, we can break this thing apart 2 different ways to combine 2 different aldehyde and Grignard reagents. Right? So we can break it apart here. Let's call that disconnection A. Or we can break it apart there. Call that disconnection B. Right? If we look at disconnection B first, right, if we're going to make that bond in the forward direction, that means we're going to have that Grignard reagent plus that aldehyde. Right? And if we go by disconnection A, we'll have a different aldehyde plus phenyl magnesium bromide. Right? And now we can take a look at these 2 reactions and see if one is better than the other. If we look at B, we can see this is 5 carbons and this is 7 carbons. Right? That's a problem, 7 carbons. I don't think we know how to make benzaldehyde, so that's probably not the way to go. Whereas up here, we have 6 carbons and 6 carbons. Right? So that's clearly a better way to make this compound given the limitations that we have. So now we can propose the synthesis. All right, so our synthesis would be phenyl magnesium bromide. Step number 1, we're going to add the aldehyde. Step number 2, we're going to add acid, and that's going to give us our target secondary alcohol. All right, so I hope these examples and strategies are helpful as you think about the problems that you're working on right now, and we'll continue to talk about this in class.